Greetings, fellow Earthlings. Today, as I promised in my previous video, we'll talk on the greatest mystery in physics of 20th century and the beginning of 21st. And this mystery is in the short question: what is quantum? So what is quantum? Famous American physicist Richard Feynman said once that nobody understands quantum mechanics, quantum theory. He included himself into this sentence. Actually, it's almost right, except one small thing. That already for half a century already, some people understood quantum mechanics, understood the roots of it. Not all the mathematics, but many mathematics too, but not, that's mathematics, it needs thousands of people. But some people understood quantum mechanics, just official science doesn't want to accept it. Exactly like my videos are blocked actually in YouTube, like my previous videos about Fermi paradox result. For those who want to understand this particular video, it's a brief video where I will just make a contours of the new understanding what is quantum. It's not the full theory, of course, but there is a full theory. So for those who want to understand it right now and immediately, you just read these three books, these three volumes, where I try to put it in a very simple way. It is a sort of a science fiction, but science fiction with formulas, like very strict formulas. They explain too the formulas of theoretical quantum physics and theory of general relativity and everything like this. It's actually very simple. Right now, it may be understood even by students of senior school. Like it was published in 98. These ideas were actually discovered, the answer for this question, what is quantum, was discovered in 1978, 1979. So it was almost half a century ago. And it was published in this book that I have shown, right? It's a very small amount of copies, so nobody knows about this book, especially in the West. It was published in Russian. This book that I shown before, this book is in English. It's translated by AI, by the way, but I edited it, of course. So what we're talking about? To understand this, please watch the previous video, Fermi paradox resolved, of myself. It will explain a lot to understand this particular message. So what's it all about? In the previous, I will make some short messages about Fermi paradox, right? Fermi paradox result means that when humans discover, and we are pretty close to that moment, when humans discover the time travel with the speed near the speed of light, or exact speed of light, and I know how to do it, by the way. My next lecture will be devoted to time machines and interstellar spaceships that actually allow to reach any distant galaxy in the universe. And we are at the edge of reaching this level of technology right now, our civilization. Maybe 20 years will need it, 20 to 30 years will be needed to adjust it, to succeed in everything, but we are at the age we understand how to do it now. So I will tell about it in my new video, right? Next video. So Fermi paradox, how it can be resolved. When the civilization reach this certain level of technology, which our civilization will reach in about 30 years, 20 to 30 years, we could travel through space with the speed of light. What speed of light is? Speed of light, many people don't understand what is it. Actually, speed of light is a very special speed. First of all, by the theory of relativity, this speed it doesn't change with the change of reference frames. So in any reference frame, the speed is the same. What it actually means, that if you're traveling to like opposite to the photon moving, right? Photon moving to you and you moving to photon with the speed of v, and photon is traveling with the speed of light, 300,000 kilometers per second, right? Whatever fast are you moving, it doesn't matter. You're still coming closer to the photon with the same speed, c. So this famous and very known formula of adding velocities doesn't work in theory of relativity if you're talking about the speed of light. Speed of light is whatever you do, whatever you move, with any speed you move, the speed of light will always be c. Are you following photon? Still c. Are you across photon or from the back? Still c. So it's absolute speed. And also this speed actually is very interesting, because when you're yourself traveling with the speed of light, the time you need to reach any point of the universe, any galaxy, whatever hundreds and thousands and millions light away, like the Andromeda galaxy, like about 2 million light years away, right? For you, if you're traveling with the speed of light, it will take zero time. It's called proper time. Proper means the time by your own watch, by the watch of the traveler. On Earth, while you're traveling to the Andromeda galaxy, on Earth will pass about 2 million years. So it's like 2 million light years away, right? So 2 million years will pass on Earth, but in proper time it will be just zero. And it's the same zero to reach any point in the galaxy, in our galaxy, in other galaxies, in our universe. Just zero. And zero is a very interesting number. And we were talking about this a lot today. So first of all, yes, and what I was saying actually in Fermi paradox resolved. Why? Because when you reach this, you actually disappear. The civilization which will start using in common life, start using this light speeds, actually it will disappear. This will happen because it will form so-called, which I call like civilization horizon. It's the same thing as event horizon that surrounds the black holes, or some other horizons they usually call the apparent horizons, but they're actually real horizons. Horizon actually, it is a surface, or not, sometimes not the surface. I would not talk about this too much, but we talk about it's the surface like a light cone, right? So if you have like this is t-axis, this is r or x-axis, right? This is space, this is time, and here is the cone. It's called light cone. The speed of light. Light goes on these lines, along these lines in the cone. So on this cone, actually, when you're moving on this cone, the actual time, proper time, will be always zero, and you can reach any point, as I already said. So what will happen after that? Why I said that all civilizations will disappear? Because the time, the relative time, is actually stopping when you're traveling with the speed of light. For yourself, nothing happens, like you're traveling and that's it. But from the observers on Earth or other distant places, like other distant galaxies, whatever, your time, the time of the traveler, will immediately stop. And when it stops, it means a lot, because when time stops, it's not only like it's written in many science fiction books and everything, that's like you're like frozen in time. It's just frozen in time, not just you. The atoms and molecules are frozen in time too. And not only this, because according to the quantum mechanics, each particle, each elementary particle or quantum, it is a wave. And the wave has certain oscillations, right? And they happen in time. So when the relative time stops, the oscillations stop too. They're not like frozen. They will be stretched. It will be like a Doppler effect. So the wavelength will be infinite, the frequency will be zero, frequency of each particle. It means that you cannot see the particle as particle. So the whole thing, the whole image of you, physical image, like a physical body, will actually be stretched and then disappear, dissolve in the thin air or thin vacuum, right? Something like this. So that's why Fermi paradox is resolved, because civilizations disappear. They travel like this in this ball of threads. This is the trajectories of all these space and time travelers. They will go like at this ball, and whatever length of this thread is, whatever it could be millions of light years, right? Still, the proper time will be zero. So they will reach each their point of destination for zero time. All of them. All of them. By the way, this resolves the twin paradox too, because the time is just zero for everybody. So they can travel to any galaxies with a zero time, return, and some of them will be going from shop to shop, like shopping with a zero time. It's still zero for both of them. So when the other will return, it will be still zero for everybody. No twin paradox at all. So reaching the speed of light is a very interesting thing. Speed of light is an absolute speed. How it goes in equations. So this is the formula of, this is the famous formula of interval or proper time, because interval, it is exactly proper time, the distance in 4 dimensions, 4D distance. It's the distance between, in four dimensions, distance between 2 points, or they say elementary events in space-time. So this is the distance, it's square root of this, right? T is time, R is distance in space. And in all my small formulas that I use the units, they're called universal units, like the speed of light is equal to the Planck constant and equal to the gravitational constant and equals to 1. So they, actually I forgot to equals to 1. And it means this, the famous formula E mc squared will be E equals just m, mass is the rest mass, and equals to omega. Remember this Planck's famous formula, h omega. So because h is Planck reduced constant is 1, energy will exactly be equal to omega. Omega is a frequency of de Broglie wave of each particle. And this is the Newton's gravitational law, right? So because the g is 1, so m divided by r, right? So when we talk about this proper time, there's an interesting thing there. If v, so there's the simple transformations, right? So r divided by t is v, the speed of the traveler. So if v equals 1, you see this is 0, and whatever t is, tau, the proper time, will be 0. So with the speed of light, proper time equals 0, whatever t is just time in the distant, for the distant observer, like for us on Earth, looking at the spaceship traveling with the speed of light. So it comes to 0. We're looking here, we can see when it comes to 0. When t is equal r, or distance, minus or plus. So distance in space with the speed of light will be minus plus t. Plus t is no interest for us. We'll talk about this later. But minus t, it gives us a clue what actually is happening with the speed of light. So what happens when distance in space equals to minus t? It means that distance in space, or space itself, it is minus t, anti-time. It is anti-time. What does it mean actually, anti-time, right? We know about antimatter, but it doesn't connect with antimatter's interesting thing. So, but we may understand what is happening when we look around us. like, for example, I'm looking at this pen, right? Or I touching my nose. At what exact point of time I touched my nose or looked at this pen? This pen is located in what kind of time? Not at the time that I imagine it or seeing it, right? It happened earlier. Everything that you see around you, all the universe, it happened before you are seeing it. All around us, everything, so-called objective universe, objective things, my objective nose or ear or whatever, or yours, right? All of these things, actually, they belong to the past. It's not even the present time, it's the past. Even the thought that we're thinking right now, it is in the past, because it takes time to realize that I'm thinking this thought. So, everything around us, objective universe, is in the past. It means what? That everything, what we see, is actually we have some distance, right? Distance not only in space, but in time. Everything that we see in space, actually it is distant from by the time. And the time is minus, because it's in the past. Plus is going to the future, minus to the past. So if you think a little deeper on this, you will see that if we have speed of light as an absolute speed, and it is an absolute speed according to the theory of relativity, right? It depends on nothing, on any frame. Whatever you do, the speed of light is speed of light. It's just exactly the same. If you do that and think on this, you will start to understand that everything that we see in the past, actually the distance, the space distance, it is minus time. R equals minus t. Distance in space equals minus time. It means that space could be, that's a hypothesis, right? The first hypothesis, that space could be actually anti-time. Let's think about it. First of all, there are other speeds, not only speed of light, right? There are other speeds. So how to deal with other speeds? The very interesting thing happened, it started happening in the, actually, it's almost in the beginning of 20th century, so it's almost a century. Physicists discussed the interesting thing which they called, because it first was discovered in a way and discussed in Germany. Germany was a very developed in science and fundamental science, very developed country. So they discussed in the first mention of this thing was in 1928, and the name was German Zitterbewegung. Zitterbewegung, or in English it's translated as jiggling of elementary particles. There were a lot of discussions for hundreds of years, you can imagine, right? But recently, some years ago, not far from today, which is the copyright, is like take a look. This is a copyright 2004. Road to Realities. Roger Penrose. It's a famous British scientist and physicist and mathematician. He found the interesting thing that he found that the main equation of quantum theory, was discovered by Dirac, British scientist, and it's called Dirac equation, right? So this Dirac equation can be split into two, like for any particle, because all the particles with the half spin, the particles of matter, right? They have half spin, half of h, half of Planck's constant. So all these particles actually are described by this equation. So it's a very important equation. All the other particles, like photon, mostly they have zero mass and they travel with the speed of light. But what about particles of matter, right? Electrons and everything. They travel with the different speeds, whatever, from 0 to something, but not the speed of light. But what was discovered in the beginning of 20th century and then transformed by Penrose, right? He found out that this, you see these zigzag motions, right? This and this. He discovered that Dirac equation could be split into two mathematically. The strict mathematics could be split into two, which explains the moving of this particle like this in zigzag motion, jiggling, or this German fancy German name, right? Zitterbewegung, correct? Zitterbewegung. So, and interesting enough, it goes with the speed of light. So what happens actually? So it's mathematics, right? So you can, it's a hypothesis, but the hypothesis means that all the speeds in the universe actually are equal to absolute speed, light speed. Because what happens? So it goes, light speed goes like on this cone, right? With this angle to the space axis, right? So it can go like jiggling, like this. Actually, if you apply another dimensions, it will go spiraling, like here, it's like a spiral. But the angle of the spiral is always, it always goes with the angle of the light cone. So this jiggling means that particle is like divided into two particles. Both of them are massless, so rest mass is 0 for both of them, but they transform one into another. And when transforming, they change their direction of moving. And they move with the speed of light. And that's very interesting, because this means precisely that all events in the universe, all the elementary events actually, because they are connected with certain type of matter, this or that, like from photons to electrons, protons, neutrons, and everything like this, and all these pieces of matter travels with the speed of light, it means that there is actually no distance between zero proper time. So zero distance for the distance between each and every event in the universe. So all events, or dots, of which the space-time continuum is made of, all these dots are actually closely connected. Not just connected, they coincide. Zero proper time means then two or 3 points, like points of the light cone, A, B, and C. We see that they are like they looks like different, right? They have space distance, they have time distance, right? Like this. Here time, and here is space, right? But in reality, they are not distant at all. They're all the same. They all coincide. Not only them. So it means that the whole cone is one dot. And this dot is like, you may well put it here, like 0. So this cone is misleading. This picture is really misleading. And that's what most of theoreticians and physicists and everybody, they miss this point. Not exactly. Mathematically it is described, but nobody was brave enough to say it like in plain words, right? In plain words, that all the light cone is just one dot, one event. And if you add this Penrose zigzag motion or spiraling motion, right, the whole universe is just one dot. Or we call it quantum. Universe is quantum. Not the beginning, not only the beginning of the universe, which like most of the physicists agreed that universe, because of Big Bang and everything, it started from one quantum, right? But even now, because all the events are still connected. And this turns upside down the whole picture of the universe. If it's like that, how we will describe such a paradoxical universe? So the question is how to describe this. And then and this was done actually in these books that I showed you. This was done. It's very mathematically, it's understandable. So how we can understand this? So the null interval, so light speeds and everything means null interval, right? Null proper time. Null interval means that all the events are identical. It's just one event. But according to the theory of relativity, we see this event like many events, like these three dots, A, B, and C, right here on the light cone. They are three different and distant, sort of looks like distant events, right, in time and in space. But because they are on the cone, they actually one dot. Actually, they are not even here, but it's somewhere here. Actually, you can put it anywhere on this cone because it's still the same, still one dot, right? And the same relates to all of other events too. So let's look at this picture. It's maybe misleading, but it says something what we see. We still see these dots on the light cone as different dots. Because like what these dots are, like A maybe Earth, right? And C maybe Andromeda Galaxy. And B, I don't know, maybe Uranus, Venus, or whatever, right? So we have them distant. Like we see the distance between them, we see the time to reach, we know the time to reach one and another thing. So we have these things different, but they are the same. What will happen in this way? If they are the same, they are interconnected. So you touch one of these events or material dots, right? Particles, you touch one of it and the other will react correspondingly because they are the same. What is this? What is this? It looks surprisingly like we have in our surroundings. We have those dots entangled. Quantum mechanics says that different events, when they are entangled, right, they're just one event which actually influence all other events entangled with this event. How to describe this kind of movement, this kind of universe? Only in probabilities. So we cannot really distinguish all these events, but we can say that one of these events, how we see them, right? It's like what we apparently see, the picture. It may have different probabilities because of different situations in this place, and this place. Universe is curved, blah, 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 all that sort of things, right? Still, so it means that they are connected, but they are connected only by probabilities. Now let's go a little further. We have this point, we say that all the light cones actually goes to one event, 0, right? Let's go further, deeper into this principle of relativity. This is the speed of light. This is a principle of relativity. That's the speed of light is the same in any reference systems, right? Physical reference systems. This is the main point of the whole theory of relativity. If we have this, we can take 0 and recall one interesting point, mathematical point. That's each 0 can be written like 5 minus 5 or 3 minus 3, right? It's very easy in arithmetics, right? Or we can write it t minus t. Remember, minus t is space and t is like time, right? So t minus t is equal 0. You may think about it like simple mathematics, but another thing, we're talking because spaces, anti-time and everything like this, it always goes like this for the time, right? For the movement with the speed of light, for the light. So if it is like this, each movement involves t and minus t. What it means? Just think a little deeper. T and minus t. It means that it goes in circle. It is a circle. And this circle explains exactly this jiggling, right? There's a spiraling because we have t, we have t moving. If t is not moving or whatever, it will be just like circle, like this. And this part is t, and this part is minus t. What is this? This is a round time. Round time. Circling time, or time loop. Time loop. And that's the answer. What is quantum? Quantum is round time. And remember, round time, it's not just for electron or proton or whatever. It relies, it describes any matter, any piece of matter in the universe. For any piece of matter, it has energy, and energy is like the time is not energy. Time is goes in loop. And what is loop actually? Right? When we have time looping, right? We have not only the loop, the size of the loop, right? But we have also amounts of rotations, right? Of this, right? These amounts of rotations measured in certain frame of reference, actually it is used to be called frequency. We have the frequency. And this is the frequency of the quantum, or it is called the frequency of de Broglie wave. Why wave? Again, what is de Broglie wave? Imagine that we have round Earth, like we have it. We have round Earth, right? But we believe for for centuries, we believe that the Earth is flat. So we start traveling on the Earth. It goes further and further and further, and actually we make the round trip, right? And we see that, like imagine that this started like we started in Africa, right? We have all black people around, blah, blah, blah. Then we crossed Europe, there are white people everywhere, blah, blah, blah. Goes further, 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 and we come to the country where again, black people. So something is really repeating. But we don't know. We thought that we're going flat, 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 flat. So we have already second place where the black people live. We decided to go further, further, go. We made another circle, we see another black people. So what we'll see when we're traveling around the Earth, around this Earth that we imagine a flat Earth. We see the waves, like black people out, black people, black, white, black, white, black, white. So when the time is running and time is round, everything goes in circles, everything goes in waves. And those waves are probability, because we see these all the points on the light cone, we see them as different, distinguished, but in actuality they are one. So we have entanglement first, and then the waves of probability second. And all these ideas are exactly goes from this formula of special theory of relativity of Einstein. Einstein all his life believed that quantum mechanics is not consistent, that quantum theory will be derived from the major absolute or sort of a universal relativity principle, the same that he formulated, or maybe generalized, right? Like not the general principle of relativity, but something else, right? So he tried to find it out. I call this the absolute relativity. I call this principle absolute relativity. And this principle is actually laid in this book. It is the real principle which we have in physics. And we have everything like here. For this oscillations, right, of time, which happens everywhere where is matter, so everywhere in space and time, so we have space-time circled. In all these events, we have this thing very well known for all kind of waves. So the size of this loop in time, like delta t, and the size of frequency, right, delta v, delta omega, it should be more or equal around 1. It's not exactly 1, but I just will write out 1 here. And this is called Heisenberg uncertainty principle, uncertainties. So the uncertainty in time is connected with uncertainty in frequency. And the same goes for space. It's like delta x and delta p, where p is momentum, right? So, so what we have now? We have now actually all of the principles of quantum theory actually derived from the simple principle, and this principle is the principle of relativity. Why all? Like, for example, all the dots in the universe, all these events and all the particles in the universe are identical. What we have in reality? We look at the electrons. All electrons are identical. This is proven in thousands of experiments. This is called identical principle of quantum theory. The same thing for protons, for neutrons, for all other quanta. All quanta are identical. They are the same. And actually it's not only the same, it's just one. But this one we see as many. This is what happens. And we see as many because we still think that our Earth is flat. Or, I mean, that's the quanta is like flat and not round, right? So actually what we have actually universe around us and the universe inside us. Inside us are many universes. All of them are our universe. It's not multiverse, very popular right now. It's not multiverse, but looks like multiverse. Each elementary particle, each quantum, it is a particular view on our own single universe. It's a view, a discourse. That's what we have. Now, how it goes with theory, right? There's a famous Bell's theorem, like, for example, which prohibits for quantum theory to have so-called hidden variables. There was a long discussion, 100 years discussion in physics about hidden variables. Like, for example, time, this is time and frequency, or position and the velocity, or momentum, right? Momentum is mass, rest mass, multiplied by velocity, right? So we have uncertainties. We have this relation of uncertainties. What it means? Well, it means that if we make a point in time small, so we try to measure exact time where this event happened, then we have the frequencies, variations in frequencies, huge. The same thing for space and momentum. If we try to make momentum measured precisely, like as much as we can, the particle looks like it stretched out, and it actually disappears, right? Because it can be found in any place in the universe, something like this. So this is what goes from uncertainty principle. And the Bell's theorem said that, okay, look, it was mathematically proven, like from the principles of quantum mechanics, it follows, it was derived that there cannot be precise measurements like of momentum and space location at the same time. No hidden variables. So there are no exact variables. The variables appear only at the moment of measurement. Okay, that was proven by Bell, but if you look into the real proof, you will see that the main point in this proof is time not circled. It was the principle of causality was the main point in the Bell theory. But we have the exactly opposite here. We have it exactly opposite. Time is circled. Time is in the loop. So Bell's theorem has nothing to do with this situation actually. So no Bell's theorem. Just a small word about, again, about frequency. And remember this formula. Energy is frequency, because H is 1, right? Energy is frequency. What frequency means in this case? Frequency means amount of returns in time. For those who read science fiction, right, who like science fiction, it's pretty obvious that the deeper you go in time, the more influential you are on the present time. The deeper you go, like there's a famous story of the science fiction writer about the guy who who killed the butterfly in the times of dinosaurs, right? Dinosaurs. And this fly changed the whole of his time. All time was gone. His time was gone. It's everybody knows that, who read science fiction, right? So go deeper in time. The deeper you go, the more influential you are on the present. Again, look at this situation. What is this? If you really can go in time, back in time, right? Because go forward in time, we know how to do it actually. If you go with the speed of close to the speed of light, you're going very fast to the future. Not in your time, but in the time of distant observers, right? So going forward in time is no question. But now we are going back in time, right? So if you go back in time, and you can change our present. So you return to your time again, back from doing something in the past, and then return to your present time. You see the changes, and the changes are the deeper you go into the past, the bigger are the changes. And what the changes are, the potential to make changes in physics, it is called energy. Energy. So what is energy? Again, the question is, what is energy? Energy is amount of distance, amount of circles that we go back in time. We go back more times, the energy is higher, and this amount is omega. It can be derived mathematically from the formulas that we have right now, from the thermodynamic and probabilities and all that sort of things. In thermodynamics, energy is proportional to the thing which is called anyway, doesn't mean what it's called. It is actually proportional to information that is recorded in the system. When we're talking about using energy, actually we don't use the energy, because energy is preserved in all physical events. Energy is preserved, so it does not change. So what changes when you're using energy, like in the car, right? You put the gas. What happens actually? The changes is entropy, or measure of disorder. So the fuel, it has much more order then the exhausted goes out of your engine. And that's what happens actually. The order is changing. So the amount of disorder, or with the negative sign, actually entropy is minus information. It's exactly like entropy, physical entropy. Physical entropy, it is minus information. That's another thing. It's a thermodynamic formula. We have it right now. It's not new. Something like this. So energy is connected exactly with omega. So an amount of circulation in our distant time, it's not in the proper time, in distant time, and that's it. So we have all the formulas of quantum mechanics. The idea of identity of the particles, we have it, right? The identity of all the places in space, right? All the spaces are identical, and that means that a particle can be found in any place in the universe. That's a quantum theory, right? The quantum theory point discourse. Why like electron can be found in each point? Because the points are the same. The points are identical for this particle, and that's why if you try to find it, you find it anywhere. Like it's just probability. It's an accident. You find it here or find it there or there. It depends upon your experiment, upon everything and all that. So you see that if you think a little deeper into the principle of relativity, you'll find all the points of quantum theory. And it was found like half a century ago, like this point in this book and in this book right now, that's published now. You can buy it on Amazon right now. So how it looks like if you go a little deeper. Everybody knows the idea, probably everybody knows who is interested in physics, right? That if you have some round curved like globe, right? And you want to put a map on it, right? You have to pull the map on the globe, but you cannot do it because the globe is curved. This is the whole idea of curved space. Curved space is objective space, right? So it's curved. If you try to pull the map on it, the map will not go. The map should be rubber, right? This idea of rubber maps, it's very popular in all the manuals of physics, of theory of general theory of relativity. And if we have a rubber, we put it on the globe, and we have the globe like regular globe with all these meridians and and parallels like we have in the globe, because it's rubber. But again, we got used to it, but and that's very familiar. But what will happen? Just ask yourself, what will happen if we don't know that the map could be rubber, could be stretched? If we still think that the space is flat. Space is flat. If space is flat, we cannot pull it on the globe or any surface. Like for example, like when we have the real quantum, like this is a piece of marble, it's actually a candy. I didn't find the marble, so it's a candy. We have a candy. It is curved, right? It's round. This one. And we have a map. The grid paper sheet. Like checker, they say the exact name for this. And we try to put this map onto this marble. How can we do it? It's not rubber, right? It's not stretching. But what we can do, we can wrap it up. We can wrap it up. We're wrapping and wrapping and wrapping, trying to put this not stretching map onto this. If it's ultra thin, we have this map. And imagine this map is infinite, so we have a lot of layers of wrap around. And what this, and you see the coordinates like this grid on the map. That's whatever you see. It is what? It is random. It is random. So when you try to pull the map on some curved object, right? And thinking that the object is flat, but it's not, like Earth. It's not flat, right? The same thing. We have this picture of that kind of thing, right? And all these are in one. All these coordinates are in one ball. It's exactly like in Fermi paradox we have. Remember, they are going the same. They're going with the speed of light. So, and this is the same thing. All the coordinates are there, and they are random. And random means probability. We don't know exact position because there are a lot of coordinates, right? But we can calculate the probabilities, and that's what all quantum theory is about. Probabilities, probabilities, and probabilities. This kind of map and wrapping, mathematically, it's not widely used, of course, but it can be used, and this is called non-holonomic or a non-integrable map. It has, of course, not determined coordinates. The coordinates are just random, and there are total different mathematics. What kind of mathematics? Exactly quantum theory mathematics, exactly. And that's what I, again, in my books, right? So I put it and found it there, and you can find it either. So what else we can say about quanta? So quanta is, I said, it's views on our universe, because when you go around and around, the first quantum is small, but the remaining, when you found many of them, they are expanding like a kaleidoscope picture, like from one point there are many points. The whole thing is bigger and bigger and bigger. This is actually in physics, it's called inflation, this process of multiplying. It is going in geometrical progressions very fast. And you have this picture. You can ask yourself, so how big is the universe? We found the universe, right, out of elementary events. So elementary quanta produced, like returning to itself, it produced the whole universe. Now this universe, how big is it? Again, you'll see it's relative. It's still one quantum, just returned to itself in time, right? So it's still one, so it's still small. And at the same time, because there are many quantums, you can say that they are huge. Because there are many oscillations, it is very energetic. So the mass is big and everything like this. So there are just two views on the same universe. And if you go to the particular loop into this, how many oscillations there are? Like, for example, there is 10 to the power of 80, 10 to 80 electrons, as I estimate, electrons in the universe. The same for protons and neutrons, something like this. So 10 with 80 zeros, 1 with 80 zeros after that. That's a huge amount. And each of them, it's a particular loop. It's a particular round time. And through this loop you see what? You see the whole universe. Each of these loops are the universe. But what's the difference? Different point of view. Different point of view. What kind of size does it have? It's easy to calculate with these rotations and all these particular things, that this size, it is called Compton wavelength. Compton like this. Compton wavelengths, and it equals h not reduced divided by mc. So this is the size of this spiral radius. The size of spiral radius. And this is, by the way, because it's connected, exactly connected with the cone, right, with the horizon. This is the size of horizon of elementary particle, elementary event. Whatever you choose, maybe electron, proton, whatever. Just you can calculate it. One more addition, this kind of picture, a big thing is created after recursive recursive move, right? Recursive returning to itself, right? This kind of picture in mathematics is called fractal. Fractals is very very extremely widespread things in the universe. Like all the trees are fractals. The fractals is the world lines or trajectories of elementary particles. Our clouds are fractals. Our mountains and the valleys are fractals. Our galaxies are fractals. Almost everything that you look around and find, it is fractal. So this idea, it is a fractal idea. This idea of fractal, another name for this fractal, it is called holography. It's a holographic principle. There is certain principle in physics, it's discussed, but it exactly connected with the fractal idea, because each hologram is a fractal. And then if you look at this, so okay, I just don't want to talk a lot about this, but like why electron or whatever quantum doesn't look like our universe, because when you go in small, you lose a lot of details. This is one thing, and another thing, each elementary particle is actually surrounded by the horizon. It's very similar to the horizon of black hole. It's not a black hole per se, but it is a horizon like this, the horizon connected with the light cones, right? So you cannot see that much into this small thing. There is a whole universe if you can go inside, but there's not easy way go inside. There is a way, by the way, it's interesting enough. So if you go inside, you can reach any point in the universe through this particular hole, right? We'll talk on this next video, where I'll describe how to build a time machine and interstellar spaceships. It's unbelievable, but it is possible, physically possible right now. Right now to start, right? Maybe 20 years we'll get all technology, make it widespread and all that sort of things, but it is possible. So what else? Just a few words about mathematics. I'm planning to make a mathematical video on that, but the best way is to read the book, because it's like a lecture. But I will make lectures, maybe not the next lecture, but after, maybe some mathematics on that. But I will tell just a few words about this mathematics, how it goes. We have a circle, right? Circle in time. How to describe this circle of time? Of course, we have probabilities too, but the probabilities, to calculate probabilities, you need equation of probabilities, right? So how to derive, in short, how to derive Dirac equation. And other some equations that are called field equations, they can be derived too. All of them are derived in these books, by the way. So how to do it? Okay, we have, like, we can write this simple picture. Like, this is past, this is present, and this is future, right? 3 points in space-time, or 3 elementary events, right? And okay, if we see that we go from past to present and then from past to future. This transformation is described mathematically as a group transformation, so-called group transformation. It's a theory of groups that describes such things, transformations. You can call it vector, but vector is a more narrow definition. So this is just a group transformation from past to present, and then from present to future, right? And then you can also find out that it can be direct transformation from past to the future. Interesting enough, and we have a so-called group operation, often called multiplication, so group operation. And group operation is just combining, the idea of combining 2 elements of the group into 1 element, right? Combining goes like this. If you denote the first past to present like I, and the present to future like J, and the past to the future like K, it will be a it will be written like this: I multiplied by j equals k. It's like vector summarizing, right? Very pictures, very simple to that, similar to that. But summarizing, by the way, or addition, right? It is a group too. It's called group of addition, right? So, but this is like multiplication, looks like multiplication, but it's still, this is not multiplication, this is a group operation, combining two elements into one. When you look at this picture, you will find out like k and k and minus k will be vector oriented different, right? You will see that e by g by k multiplied, right, by j by k equals -1. 1 is this circle, -1 is this circle. So we have this algebra, simple algebra, out from the simple ideas of past, present, and future. That's present, have two neighbors, one in the past, one in the future. And we have these things, right? And E, J, and K are called imaginary units of quaternions. It's a famous thing discovered in the 19th century by William Hilbert. And they have lots of usage in modern mathematics. Mostly not like quaternions, they are transformed from this a little, but it's all started from Hilbert and quaternions. All the modern mathematics of used in physics too, they started from quaternions. So quaternions are very in the very root, and you see that quaternions actually describe our loop in time. So these multiplications, it describes this our loop in time. But we know that space is anti-time, right? So there should be certain quaternions, the same, but they behave differently. But the same quaternions for the space. So we have three, we may say, dimensions of time: past, present, and future. They are dimensions because they may be measured separately. Why? Just like, for example, that, like, look at our society. We have in our society we have young people, we have old people, and we have adults, grown-ups. So adults are present, right? Young are future, and past are old, right? So, and we can count each of them separately. There are certain amount of old people, certain amount of grown-ups, and certain amount of young people. So they are different measurements, and they may be called different dimensions. So there are three different dimensions of time. They are in a certain way, mostly, they're independent of each other, which is called orthogonality in mathematics. Orthogonality. Just like this, right? Oh, sorry, how like this, right? Like cross. Orthogonal. You know, like this. T and R are orthogonal here. So we have three dimensions. So in space we should have three dimensions too. In space we have three dimensions. So this is explanation. Another explanation goes from this simple picture. Why we have three dimensions and not two, not one, not four, right? We have three dimensions in space simply because we have three dimensions in time. And three dimensions in time means that present have two neighbors, past and future. And that's all enough to say this. By the way, quaternions, they describe mathematically the rotations in three dimensions. So rotations in space and the rotations in this circle of time. So this is an ideal thing to use in mathematics of this loop theory, the theory of round time, right? So we have three dimensions in time, it's E, J, K, and also we have three dimensions space. So we should have both of them. They're separate, right? So they're independent certain way. So it is called biquaternion. It's called biquaternion. And B quaternion is a quaternion with the complex coefficients. I wouldn't describe it there, I will describe it later. But in these B quaternions, very easy from this point of view, very easy in just a few steps, very simple steps, which are actually the first time I wrote it in this book in written in 1978 and published in 1998. So, and this equation, it looks like this, where sigma and now this is nabla. I wouldn't describe this. This is Dirac equations. Dirac equation. It describes the behavior of all matter particles here. Okay, what else to say about this? So Dirac equation is pretty easy, but not of course not derived right here. What we can say else to this? This circular motion, it's not motion of matter, right? Because matter actually, it's also maybe considered a carrier of information. So carrier of information means that if you go in circle, this is the system, material system, which knows itself. It's a loop of consciousness. It's a subject. So we may say that a very simple way, in a very simple way, not like pretty primitive way, but anyway, and like remember this holographic principle that's in small, there's a lot of like hologram. Oh, that's in hologram. I should describe one other interesting thing, because all this fractal picture, it exactly gives you the understanding how hologram works. Right? For example, a mirror. It's in a way it is a hologram, believe it or not. You have reflection in mirror. In mirror you can reflect the whole universe, right? You turn mirror to the stars and you will see stars, right? And now you break the mirror into pieces and take any piece of the mirror you can take, and again you turn it to the stars, look closer, and you will see the whole picture, the whole universe again. And each hologram is exactly like that, exactly. So this circle is a mirror, like our brain. It's a mirror of the universe, but it is independent and it is protected by the horizon. Horizon does not allow information to go out directly. It goes out in a very transformed way. So it is sort of a private thing. It has consciousness. It is self-aware because it knows that it's there. In a certain way, it has a free will, which we call randomness, which we call probability of quantum mechanics. Of course, because of there's the theorem that's if the amount of information is huge, it is this is a mathematical theorem in theory of communications. So if the amount of information is huge, you cannot distinguish it from randomness. That's what's happening here. And plus the horizon, which actually close the flow of information, like read about black holes. There's no information goes from black hole. Exactly the thing happens with each quantum. Quantum does not allow you to know a lot about this inside, but inside is our own universe. Okay, so that's probably finish it. Like, oh yeah, maybe I will say a few words. These small things, they're called Seides, by the way. I just read a book, interesting book by the Federico Fagen. He's the inventor of, actually, believe it or not, the first inventor of first silicon chip. He wrote an interesting book which is called Irreducible. And he called such systems like quantum systems Seides. So maybe it's a good word, Seide. It's like identity. So I hope he will see my videos. I hope, maybe not, we'll see. So he's going in many ways, he's going very close to what I'm saying, not here, but about the sati, self-awareness, consciousness, and everything like this. So again, I'll show you the books, right? So read the books, 3 volumes of them, enjoy. They're written in science fiction way, but with a lot of formulas. I showed it to you, the formulas here. There are lots of, you see, like this. So there are formulas of general relativity and quantum theory and all that sort of things. And what? See you again. Thank you for listening.